So your warm up for today, it says Maribel has $7.25 in her pocket. She has a total of 35 coins, quarters and dimes only. How many of each does she have? So go ahead and set up a system and you're going to go ahead and solve it. So today we're going to go ahead and start talking about exponential functions and their graphs. This will not be on your test on Friday. Instead, this information will be on the following unit's test. But in order to make sure we don't get behind schedule, we're going to go ahead and start today. So exponential functions, the parent function for an exponential function is f of x is equal to 2x. An exponential function has base b. Remember, the base is the number that the exponent is being applied to. And a cannot equal 0. B has to be greater than 1. B cannot equal or greater than 0. B cannot equal 1. And x is any real number. So the base b is a constant and the exponent x is a variable. A, whenever we have the function f of x is equal to a times b to the power of x, a is going to be your initial amount or starting value. So just like I said, I would like you to write this down. A is your starting amount. B is what we call the growth factor, and we will spend a lot of time differentiating between growth factor and growth rate. And T is the time. And just like I said before, there are some stipulations to this. A cannot equal 0. B has to be greater than 0. B cannot equal 1. Doesn't mean it has to be greater than 1. It just can't equal 1. And then X has to be any real number. So we have this graph here, and we're talking about exponential growth. So exponential growth, we see that as we move from left to right on the graph, we are increasing. Our y-intercept of the parent function here is at 1. And the domain goes from negative infinity to positive infinity, or it's all real numbers. But one thing we will talk about is the range is going to be y is greater than 0 or 0 to infinity. The reason for that is because we have a line that is called the asymptote, and the asymptote is a line that our exponential function graph will get closer and closer and closer to, but it will never touch. So this is called a horizontal asymptote. It's y equals 0. So as this graph continues, it's going to get closer and closer and closer to 0, to which the y value is like 0.000001, but it's not actually touching 0. An asymptote, the definition of it, is a line that a curve approaches but never touches. It will never, ever touch that line. So now we're going to talk about an exponential decay function. So in this situation, now instead of increasing from left to right, we are going to be decreasing from left to right. Our y-intercept is still 0, 1 in this parent function scenario. Domain is still going to be all real numbers. The range is still y is greater than 0 because we have that horizontal asymptote, or the line that we're going to get really close to but never touch. So graphing exponential functions, this is what we're going to practice today. We have f of x is equal to 2 to the power of x. What we're going to do is we're just going to plug in some values for x and then find the y values so that we can plot points. So when I plug in 0, everything to the 0 power, remember if I plug in 0 here, anything to the 0 power is 1. So our y-intercept is going to be 1. If I plug in 1 as my x value, well, 2 to the first power is 2. And then if I plug in 2, it's going to be 4 because 2 squared is 4. As I get closer and closer, further along the x on the left side, we're going to get closer and closer to 0. So if I plug in 1, negative 1, that would, remember, negative exponents send us down to the denominator. So this becomes 1/2. So negative 1 is at 1/2. If I plug in negative 2, we're going to send that down to the denominator. It would be 1 over 2 squared, which is 1/4. So calculator comparison, you can plug these in the different y values and you can notice the trend. So the blue line here is y equals 2 to the x. Our orangish red line here is y equals 5 to the power of x. And green is y equals 10 to the power of x. Notice that the higher the number underneath the exponent, the steeper the curve of the graph. So exponential growth is increasing. The bigger the base, the steeper the graph. The horizontal asymptote for all three of those was still y equals 0. And the x-intercept was none. The reason for that is the x-intercept is where we touch the y-axis. Well, if I have a horizontal asymptote at y equals 0, it means this graph is never going to touch the y-axis or the x-axis because it's going to get closer and closer and closer to 0, but never touch it. So we have no x-intercept. The y-intercept was at 0, 1 for all of these graphs. The domain was all real numbers, and the range is y is greater than 0 because we have that horizontal asymptote that we're never going to touch. So when the base is a fraction, I can plug these in. We have an exponential decay function when we have a fraction base, and notice as the fraction increases, our curve gets flatter and flatter. That's what's happening here. So what happens? Exponential decay is decreasing. The bigger the fraction as the base, the flatter the graph. Still had a horizontal asymptote at y equals 0. The x-intercept, there was none because we're not touching the x-axis because we have that horizontal asymptote at y equals 0. The y-intercept was still 0, 1. The domain was all reals, and the range was y is greater than 0 because of that asymptote. I would like you to make this table. We're going to make the graph. Go ahead and plot some points. So y is equal to 2 to the power of x. We're going to plug in the numbers I asked for. So first things first, we're going to plug in -2 for x. When I have a negative exponent, it forces our base in exponent to flip where they're at. So currently it's in the numerator, so it's going to go down to the denominator. So then I have 1 over 2 squared, which 2 squared is 1/4, okay, or 0.25. Then I have -1, again, 2 to the power of -1 forces that base and exponent to move down to the denominator. That would be 1/2. Plug in 0, anything to the 0 power is 1. If I plug in 1, 2 to the first power is 2. And if I plug in 2, 2 to the second power is 4. I can then plot those points on a graph, and our curve would look something like this. Since it's increasing, this is an exponential growth function. The y-intercept is where we cross the y-axis. That would be at 1. The domain is going to be all reals. Our range is going to be y is greater than 0. And the asymptote, remember your asymptote is the equation of a line, so it has to be y is equal to 0. Our second example here, we have y is equal to 1/2 to the power of x. So I'm going to plug in -2 when I have 1/2 to the power of x at -2. That's going to be 4. And you can plug this in the calculator. You don't have to do it in your head. You can go ahead and use your calculator to help you. So when I put in -1 for my exponent and put it in the calculator, I would get 2. Anything raised to the 0 power is 1. Well, 1/2 to the first power is still 1/2, and 1/2 squared will be 1/4. So notice it's pretty much the exact opposite graph as what we had in the last example. This would be exponential decay because as we read from left to right, we are decreasing. The y-intercept is still 0, 1. The domain will always be all reals. And the range, we still have that asymptote, so y is greater than 0. And our asymptote is y is equal to 0. You must write it as an equation. The asymptote is just not a number. It is a whole equation of a line. So we should be saying y equals. For this one, we have y is equal to 3 to the power of x. I'm going to plug in our numbers. So if I plug in -2, that would be 3 to the power of -2. When we have a negative exponent, that sends our value down to the denominator. 1 over 3 squared would be 1/9. If I have a -1, again, sends it down to the denominator. That would be 1/3. Anything to the 0 power is 1. 3 to the first is 3. And 3 squared is 9. If I plot those points on the graph, it would look something like this. It is increasing over the domain as we move from left to right. The y-intercept is still 0, 1. Our domain is all reals. We still have that asymptote, so our range is y is greater than 0 because that graph will get closer and closer to 0. It looks like it's going to touch it, but it won't. And our asymptote is y is equal to 0. Okay, next one, a little bit more complicated. I'm going to go ahead and plug into the calculator. We have 2 to the exponent of -2 minus 1. That gets me -3/4. 2 to the negative first power minus 1 would be -1/2. 2 to the 0 power is 1. 1 minus 1 is 0. 2 to the first power is 2. 2 minus 1 is 1. 2 squared is 4. 4 minus 1 is 3. So notice we have shifted our graph here and we are no longer sitting where we once were. It is still increasing over the domain because as we move from left to right, it is going up. The y-intercept now is at 0, 0 because I've shifted my graph down. The domain is still going to be all reals, but this time our range, the graph is going to get closer and closer to -1, so y is greater than -1. Our asymptote is that line we get closest and closer to, so y is equal to -1. Our fifth one, here we go. We have 1/2 to the power of x plus 3. If I plug this in the calculator with -2 as my exponent, I will end up with 7. If I plug in the calculator, we're going to get 5. Anything to the 0 power is 1, so this becomes 1 plus 3 is 4. Then we get 3.5 and 3.25. So now we've really shifted our graph in a different direction. As we move from left to right, we are still decreasing. Our y-intercept, however, is now 4. Domain is still all reals. The range, what value am I going to get closer to? So really it's the option that's one below your y-intercept. So I'm going to end up getting closer and closer to 3. So y is greater than 3. The asymptote is going to be that line, which is y is equal to 3. The number for your range and the number for the asymptote should be the same. If they are not the same, you did not do it correctly. Okay, do the values represent an exponential function? Why or why not? So basically, you're asking yourself, do I have a constant rate of change or do I look like I'm multiplying by multiple things or squaring something? So to go from 1, I multiplied by 5, then we multiplied by 25, and then we multiplied by 5 again. So instead of adding by the same thing every time, we are multiplying. So yes, it is an exponential function because the y values all multiply by 5. For the second option, I go from 81 to 27 to 9 to 3. Yes, it is decreasing, but remember if you multiply by a fraction, like if we think back to sequences, it is decreasing. So it is an exponential function. I'm just happen to be multiplying by 1/3. For the next one, to go from 3 to 9 to 15 to 21, well, I'm not adding the same thing every time, but at the same time, I'm not multiplying by the same thing, so it is not an exponential function. Oh, excuse me, we're adding 6. I miscalculated. The next one, we're going from 2 to 4 to 8 to 16. Well, yes, it is because I'm multiplying by 2 instead of adding. When you are multiplying by the same number on the y's, it is an exponential function. When you are adding, it is not. All right, we're going to shift gears a tiny bit. We want to talk about exponential regression here. You already know how to do the majority of this. It is the same format as linear regression. However, instead of hitting option number 4 when we want to go calculate, we're going to choose option 0. So I've written out this table and I'm going to go ahead and change to where you can see my writing. So basically, I don't know how many bacteria were in the initial sample value, but instead I have all these other data inputs. So I'm going to use my calculator to help figure out what we had. So I'm going to turn my calculator on. First step is to clear the list. So second plus 4, enter. Then I'm going to go into stat. Same thing like normal. We're going to start in edit. X values in list 1, Y values in list 2. Now, I don't have a Y value currently for 0, so do not put 0 in the table. So instead, I'm going to do 1, 2, 3, 4, and 5. And we're going to right arrow and put our Y values. So we have 40, 75, 150, 297, and 510. Okay, we are calculating exponential regression, so I'm looking for an equation to give us a good estimate of or prediction for this exponential function in sample. So we're going to go to stat, right arrow to calculate. Now this is normally where we would choose option number 4 for linear, but we're not doing linear, we're doing exponential. So we're looking for is option 0, which is exponential regression. Hit enter, same thing till the screen changes. So now we know that exponential functions are written in f of x is equal to a times b to the power of x. So a here is our y-intercept, our initial value. So we have f of x is equal to, we're going to round, because it's bacterial, we'll round to the whole number. So I'm just going to say this is 21. Parentheses, and then we'll go ahead and leave it as rounding to the whole number again. So 1.9, we'll round that to 2. Okay. So it asks for the initial value. Remember, our A value, or this first number here, is going to be our initial. So the initial number, I'm going to go ahead and say, was 21 bacteria. So the next thing it's asking is how long until it reaches 1 million? Well, 1 million would be a Y value because we're talking about bacteria. So to calculate this, we are actually going to go ahead and use our function on the Y equals. So I'm going to type our equation. So we have 21, whoops, still in the equal sign, 21, parentheses, we have 2. We're going to use your caret symbol, raised to the power of x. And now I want to find 1 million, so I'm going to do second graph. So I can look at the table. As you can see, these numbers are going to get really big really quickly. So remember, a million has 6 zeros after it. So I'm looking for the first time we have scientific notation to the 6th place, and that would be at 16. So it will take between 15 and 16 hours to reach 1 million, because 1 million is the Y value. Now, then it asks me how long after 10 hours, so I can just go ahead and find X for 10 in our table, and we're going to get 21,504 bacteria after 10 hours. One of the hardest parts about exponential regression is more interpreting it and whether I gave you an X value or a Y value. So you can always come up with your equation, then you can plug it in Y equals to be able to answer some of the questions about it. All right, for today, there is an exponential regression activity on Canvas. Then we have homework 3-7, which will be due next Tuesday, and your test will be on Friday.